Today we're going to be talking about airfoils and lift. So hopefully after this lecture, when you look at the cross-section of a wing, it will not look the same to you anymore. So instead of just seeing shapes, I hope you can see vortices and sources and where the flow would accelerate, where the flow would stagnate, right? And things like that. So let's see how we can get to there by just manipulating the very simple fundamental elements we have studied on Monday, right? Remember, there are 3 fundamental building blocks of an incompressible potential flow. What are the 3 elements? The first element is very simple. What?
Vortex.
Oh, vortex. Actually, that's the second component. It's not even the simplest component. Free stream, right. The first one is free stream. It's just a uniform velocity. It doesn't have to be just along the x direction. It can have a component in the y direction either, right? So uniform velocity is the first component. Second component is a vortex. The vortex has really 2 parameters, actually, like one scalar parameter and one vector parameter. The scalar parameter is its strength. The vector parameter is the location of its center, right? X and Y. So you can just put vortices of different strength at different locations. And the third fundamental building block was what? Sources or sinks, right? I mean, if the strength is positive, we call it a source. It spews flow out of a singularity. If the strength is negative, it's a sink. Basically, it sucks flow into like a black hole, a singularity. All right. So today we are going to see how do we use this to build airfoils. But first of all, why do we care about the shape of airfoils? Well, it turns out the shape of the airfoils has a lot of impact on airplane performance. So this is just a very simple calculation of just a fuselage plus a wing. And if you look at the airplane, these 2 airplanes, they look almost exactly the same, right? And you are going to see it next slide. So basically a simple fuselage plus a single wing. And these are the 2 different airplanes. I mean, if you scroll up and down, no difference, right? The only difference is the cross-section of the wing. One is Knockout 0012 airfoil. It's a symmetric airfoil. And this is probably, I would say, the most common airfoil like used in symmetric applications like vertical tails, for which you don't know, I mean, you don't want to emphasize the flow coming from one side versus the other side. The other one is 4412. So the thickness is exactly the same, except for there is some camber, not even significant, like 4% of the chord length. The maximum camber is 4% of the chord length. That's what the first 4 means. Is the maximum camber as a percentage of the chord length. The second 4 means actually 40%. So that's where the maximum camber is. The last two digits are thickness. So these 2 airfoils actually have the same thickness. But if you look at the drag versus lift curve, they are quite different, right? And we're going to see throughout this subject, not just in this class, right, what is really making that difference. And in particular, you see that the symmetric airfoil, when you are trying to get a larger lift coefficient, the drag is going to be much higher. Okay, and if you translate that into L over D, that's what it looks like, right? So, and this should be very familiar, right? Especially if you take unified and if you remember what we talked about in the beginning of this course, when we were talking about induced drag and the skin friction drag. All right, at a low CL, that means if you have an airplane that flies, that has the same weight, right? And if you want to fly fast enough to have the lift balancing its weight. So at a low CL, that means you have to fly at a higher speed to get to that lift, which means your skin friction drag is going to be high, so L over D is going to be smaller. When you have too high of a CL, that means you have to, you are flying pretty slowly, right, to generate the same lift. And when you are flying slowly, you get more, what kind of drag? Induced drag, right? Because you are flying slower, you are pushing less air per unit amount of time, right? And because you want to get the same momentum by pushing less air, you need to push the air a lot harder. And pushing air harder requires energy, right? You are spending more energy pushing air harder downwards. So the L over D drops. But somehow there is this pretty large gap in L over D at the high CL range. And even at low CL range, the L over D is different for these two airfoils. So we'll be looking at what is really making such differences. And on the high CL range, the difference is actually pretty easily explained. So this is really the flow field computed using, I think this is the first time we see a computational fluid dynamics result, right, in this course. So here is essentially a simulation of an oil flow on the surface of this airplane. So like in wind tunnels, you can basically put oil on top of these surfaces, and the oil would basically flow along the direction of the skin friction, right? It's very similar to like if you are driving in a car in the rain, you're going to see kind of the water on your glass is going in the direction of the flow. So that's basically indicating the direction of the flow. And the color represents the magnitude of the skin friction, right? So when you see red, it means the flow near the surface is going fast. When you see blue, it means the flow near the surface is going slow relative to the surface. So what you see is here, there is this blue region where the flow just swirls. That's called the flow separation, okay? So essentially you have this region where the flow goes near the surface, goes in the opposite direction, right, as the upstream flow. Okay, so this at higher angle of attack, the flow separation is making this NACA 0012 airfoil perform less well than the NACA 4412 airfoil, which has attached flow at the same lift coefficient. So we'll begin to study why some airfoils are more resistant to flow separation, and we'll see it's because of the pressure distribution, right? So today we'll be looking at what is determining the pressure distribution on the airfoil. And after a few weeks, we'll then study how the pressure distribution is going to affect flow separation. But the shape of the airfoil does a lot more than determining if the flow is going to separate or if the airplane is going to stall or not. So this is another very critical aspect of how airfoil shape determine performance. That's stability. I usually get, about half of all the students, or half of you, have a really hard time reasoning about when an airplane would be stable or when an airplane would not be stable. So this is usually the kind of graph we use to determine stability. Okay, on the x-axis is either lift coefficient or angle of attack. Right? Usually lift coefficient goes up as you increase angle of attack. On the other axis, it's either the center of lift or some kind of moment around the center of gravity. Okay, so the question is, what kind of slope do you want to see for the airplane to be stable? Would you want the center of lift to shift I mean, by the way, this is the negative, but like okay. So anyway, so do you want the center of lift to shift downstream as you pitch up, or do you want the center of lift to shift upstream as you pitch up?
Is it downstream? So it goes upstream and you're then going back.
Exactly, right? So that's good. I know, like usually like half of the class gets it, but somehow. So basically, let's imagine if the airplane is flying that way, all right, and you just touch your control and make the airplane pitch up a little bit. Now the center of lift, as we're going to see a little bit later, the center of lift depends on this angle of attack, right? So if you pitch up a little bit, the angle of attack increases, you get higher lift. But more important is where that higher lift is. If the higher lift has a contribution upstream, it'll push the airplane up, nose up even more, right? So if you pitch up more, the lift makes the airplane pitch up even more. You have an unstable situation. Similarly, if you pitch down, you don't want the center of lift to shift backwards. If as you pitch down, the center of lift shifts backwards, it is going to make you pitch down even further. It's another unstable situation. So what you want is the center of lift from nose. I think I made a mistake in labeling here. This is actually should be plus. Okay, so you want the center of lift from nose as you pitch up to increase or decrease. You want the distance of the center of lift from nose to increase because you want it to shift downstream as you increase angle of attack. So on the blue and orange airplane, which one is more stable? The blue is more stable, right? Sorry for this negative labeling, but this way is more downstream. This way is more upstream. Right? As you increase center of attack, increase CL, you want the center of lift to go backwards. Okay, so this is very critical. The NACA 0012 airfoil is almost neutrally stable until you get to higher angle of attack, which you gain a little bit of stability. While the NACA 4412 airfoil is very unstable, especially at low CL. All right, so the shape of the airfoil affects stability a lot, right? So, for example, like we all know in that by adding a vertical tail, by adding a horizontal tail, right? If you pitch the horizontal tail in a good way, like have a lower angle of attack than the main wing, you gain stability, right? But there are a lot of flying wing designs that doesn't have any horizontal stabilizer nor canard, right? These flying wing designs basically achieve stability through the shape of airfoils. So this is something we're also going to study, how airfoils affect stability. So that is how the shape of the airfoil affect whether the center of lift shifts upstream or downstream as you pitch up and pitch down. Okay, so that's the two things we'll be studying. One is the pressure distribution, which is going to affect stall. The other is how the pressure distribution is going to change as you pitch up and down. So, the pressure distribution is really the primary thing that drives not only how much lift you get, but also where that lift is. So, for example, this is the symmetric airfoil, and this is the cambered airfoil. And here you see the pressure distribution. So red is high pressure, blue is low pressure, right? On this symmetric airfoil, can you see from this graph roughly where the center of lift might be? And compare this with the cambered airfoil. Which airfoil has the center of lift closer to its nose? The first one, right? Because it gets a lot of suction near the leading edge. And it's the suction on the upper side of the airfoil, the wing, that creates primarily responsible for lift. We're going to see later that there is a high pressure region at the stagnation point below the wing, but the primary contribution to lift is the suction on the top of the wing, right? So basically, suction on top, low pressure on top of the wing makes the streamline curve downwards, right? As we see that from the Top Gun movie and all kinds of exercise we have done before, that as the airplane passes, the flow behind the airplane goes down, right? What is causing it to go down? Primarily, it's this low pressure region. This low pressure region makes the flow accelerate in the curved line, accelerates downward. And it's the downward velocity after the airplane passes, or as the flow goes behind the trailing edge, that is primarily responsible for the downward motion of the air behind the airplane. But where that primary suction is depends critically on the shape of the airfoil. So for this airfoil, right, the primary suction is near the leading edge. But for this airfoil, the primary suction is somewhere, it's still towards the more closer to the leading edge than the trailing edge, but it is less close to the trailing edge than the symmetric airfoil, right? Why is that? What is determining that? So that's what we are going to be starting to look at this class. Okay, so this is just another animation of computational fluid dynamics that really illustrates what the computed flow is like around an airfoil, right? So basically, as the angle of attack changes up and down, you get you get the pressure force, but primarily you get much larger suction force, right? That is primarily responsible for accelerating the flow orthogonal to the direction of the free stream. And essentially, let's actually start to figure out the physical mechanism of why that is the case. All right, so let me start. How many of you have your laptop or tablet? Okay, all of you. Anybody don't have it? Okay, good. So if you can just bring up your laptop or computer, and you all have access to the OneNote link, right? I think if you go to Canvas, it's on the syllable, right? On the first page on Canvas. So you should have access to that link. So if you click on the link, this is what you're going to see. So I have already populated a bunch of sources. And some of the sources, basically they are uniformly spaced from 200, which is the whole canvas is 1,280 something long, and I have uniformly spaced the sources from 200 to 1100. And I've populated the strength to be 2 upstream and -2 downstream. The question is, what do you see this collection of sources and the sinks, right? What kind of airfoil am I simulating using this set of sinks and sources? And does it make sense?
Where's the link for that?
Okay, the link to the... Yeah. Are you looking for the link to the OneNote, or looking for the link to the web page?
I guess whatever link I need.
So if you go to Canvas, and on Canvas you go to the syllable, right? There is a OneNote. So basically, that link takes you to all the notes I've been kind of writing in class. Now, if you go to that OneNote notebook and scroll to the second module, that's the incompressible potential flow module, and we are at the second second section of that module, right? And I think this page is probably the fourth page or something, right? If you go to the oh, it's the sixth. It's the seventh. No, the seventh page. Yeah. So the third one from bottom, if you go to OneNote, so what we are at is the second section at module 2 and the third page from bottom. That's how to calculate symmetric flows around airfoils. So if you click the link at the top, you should be able to get to that web page. Yeah. Have you got there yet? How many people are still looking for? You're still looking for the link? Let's see. Oh, you got it? Okay. All right. So you should all be at a page that looks like that, right? Okay. Everybody at this page, the same page? Okay. So what kind of shape are you seeing here? Huh? It's symmetrical, right? And any particular what does the airfoil look like? Just looks like a diamond shape, right? So basically, it's an airfoil that just thickens as you move downstream at almost a uniform rate, and then thins out towards the trailing edge, also at more or less a uniform rate. So why does that make sense? I mean, if you look at how can you correlate the shape of the airfoil with the strength of the sources and sinks? For example, let me challenge you to change the shape of the airfoil from a diamond shape to a hexagon. So I want to just trim the top and bottom of the airfoil from maybe 1/3 to 2/3 into flat surfaces. How would you do that? How would you change the source and sinks to do that? Yes?
I'd put stronger sinks in the middle, about 3.
Put stronger sinks in the middle, like here in the right in the middle.
Yeah.
So if I make it 3 or -3? -3. Let me just show you what happens if I put a very strong sink in the middle. Right? A strong sink in the middle basically sucks flow in. So if I put 3, I might not see the effect so strongly, but it's no longer going to be a closed airfoil. So again, think about conservation of mass. Why did I put the sum of the strengths to 0 in the beginning? Think about conservation of mass. If you put a control volume over the entire section of the entire set of source and sinks, right? What is the total mass flux? Should be the sum of all the strengths, right? Remember, like we are composing a flow by linearly adding all of these components. Okay, if you draw a control volume around any individual, okay, so if you draw a control volume around just a free stream, right, there should be no mass flux. If you draw a control volume just around this source, you should get a mass flux out of that control volume with a total mass flux rate of 2, right? If you draw around these two sources, you should get a mass flux of 4. So if you want a total 0 mass flux, which is what should happen, right? If you have a physical airfoil, you should have the strength to be added up to 0, right? That's the only way to make the airfoil, to make the flow field a physical flow field around an actual airfoil. All right, so it's a very good idea to try, but just doing this would make it actually non-physical. So it's not obvious because the strength is pretty small, but what you can see is that the streamlines actually terminates before the last sink, and the last sink therefore sucks a little bit of flow that came from the free stream, right? If you put a -3 here. Okay, any improvements to the idea of how do we make it a hexagon? Yes?
You could take the middle one that I think was initially 0 and set on each side, a couple of sources and sinks to 0 strength.
So I can still keep the middle one to 0, right?
Mm-hmm.
And are you suggesting I also make, like, how many of them do you want me to make 0?
Maybe 3 on each side.
3 on each side, okay. So 0, 0, 0, and 0, 0, 0. And see how the shape changes. So what you're effectively doing, right, is to remove the mass that comes out of several sources upstream, and also remove the mass that goes into a few sinks downstream. Right? It makes perfect sense. So that you can see like these, the upper surface and lower surface around these 0 sources and sinks now becomes parallel to the free stream. Right? So that makes sense in terms of if you think about how does the source and sink affects the velocity field. I was asking you to make the shape of the airfoil to be straight, to be parallel to the free stream, right? And if the shape of the airfoil has to be parallel to the free stream, that means the velocity in the y direction has to be what? Has to be 0, right? Okay, now think about how the source and sinks affects the velocity here and here. If you have a source, if you have a sink, if you have a source of strength non-zero here, let's just try it right in the middle, right? If I have a source of strength 10 over here, it affects the velocity over here, right? If you hover your mouse over here, it makes the v velocity positive by remember, like the contribution of a source to the flow field, right? The v contribution is proportional to y, divided by x squared plus y squared, right? Times the strength of the source. So basically, it makes a positive contribution here and a negative contribution here. So a positive source here makes the airfoil thicken at this location. And a negative source here or sink here makes the airfoil thin out at that location, right? The v velocity is going to be the v velocity is going to be now negative, and that means the flow always has to be tangential to the airfoil, right? So the airfoil thins out at that location. Okay, any questions? Okay, if no questions on that, you can type the name of an airfoil. So what I want you to try is 0012. So that's the symmetric airfoil we have been looking at in the previous calculations. Can you change the strength of the sources and sinks? Okay, so here's what I ask you to do. keep all the location except for the first one. You are free to move the first location of the first source a little bit in the streamwise direction, up or downstream or upstream, right? But keep the location of the other sources exactly where they are, and only change their strengths, so that try to get the flow go tangential to the entire NACA 0012 airfoil. All right, so I'll give you some time to do that. Do you understand what principle we are using, right? We are not changing the strength blindly, right? We are using the principle that you put a positive source if you want the airfoil to thicken at its neighborhood. We put a negative source if we want the airfoil to thin out at the neighborhood. And if the airfoil thickens very rapidly, we want to put a large source, right? If it thickens very gently, we put a smaller source. If it thins out very fast, we put a larger sink. If it thins out slightly, we put a smaller sink. It doesn't have to be perfect. How many people got it close enough? Oh wow, good. So I hope you get something similar to what I got. No, which is this one. Yeah, so what I got is the distribution starts from 10, and I moved it downstream a little bit, goes 6, 2, 1, and a bunch of zeros, and started as -1, -2, and all the way -2, right? So if you look at the numbers, they are pretty proportional to the rate to the derivative of the thickness, right? So if you look at the shape of the airfoil, oh, I didn't even type in. So this is pretty much the NACA 0012 airfoil, right? So whenever the derivative of the thickness is high, I have a high strength source. Whenever the derivative is almost 0, right? As I go downstream a little bit, so these around here, the derivative of the thickness is almost 0. I have a 0 strength source, right? As I go further downstream, the thickness starts to decrease. That means the derivative of the thickness with respect to x is now negative. So then I have a sink. I have a negative strength source, right? So that makes sense, because when you have a flow spewing out, it makes this portion bounded by the two streamlines that come from the stagnation point to be wider, right? And whenever you have things sucking flow in, you make the stream tube narrower. That's basically conservation of mass, right? Basic conservation of mass. Okay, so if you draw a control volume that ends over here, how thick the airfoil is proportional to how much artificial mass, right, you are injecting into the flow field. Okay, any questions regarding to that? So essentially, we can basically place sources and sinks to simulate the flow over any symmetric airfoils. And what is the result of that? The result of that is we can now analyze the flow field, right? Where would the flow be accelerated? Where would the flow be decelerated? For example, over the leading edge, of course, you have a bunch of sources opposing the free stream. So you get a stagnation point. The pressure is going to be, if I go exactly, it's very hard, but like it should be 0.5, right? Because it's half of rho, which is equal to 1 times velocity magnitude squared. And here the velocity magnitude is 0, comparing a velocity magnitude of 1 free stream. So the difference in pressure is actually 0.5, right? Okay. on the other hand, especially when the stream tubes are widening, okay, you get a contribution of the sources to the y velocity. That adds up with the x velocity to make the flow go faster. So when you see a large source, especially for example around here, just above this large source, you have a negative pressure. So that's starting to be a suction. And then if you go downstream a little bit from this large source, you get even lower pressure, because now this source is not only contributing the y velocity, but also pushing the flow along the x direction, right? Okay, so the fastest speed really comes from a little bit downstream of the high strength sources. So negative 0.19. So that's where the flow accelerates the most. And if you're designing airfoils, the way to think about, the way to reason about how, so when you, let me go back. When you're designing airfoils, you don't think about what shape I want. You think about what kind of pressure distribution I want. Because it's the pressure distribution that, one, determines how much lift you get. It determines, but by the way, the pressure distribution means how the pressure changes along the contour of the airfoil. Okay, it determines how much lift you get. It determines where the center of lift is, right? Because if the pressure, if there has a high suction over here, I mean, I don't want to focus on this airfoil because it's symmetric, right? So however, if you have a suction here, you have an equal and opposite suction over here, so it cancels out. But in general, when we're going to be moving to non-symmetric flows very, very, very soon, like in like 5 minutes, you are thinking about where the suction is, because that determines where exactly your lift acts, right? And as you change the angle of attack, is that lift, is that peak suction moving downstream or upstream? That's very important. Okay. And also the distribution of pressure, as we are going to see a little bit later in viscous flows, is going to determine very much whether the flow is going to separate, where it will separate. If you are moving along the solid surface, the pressure increases pretty suddenly. That's a location where the flow might separate. Okay, that's another thing that why we're thinking about pressure distribution. So you think about what kind of pressure distribution you want, or how do you want to change the pressure distribution. And that actually translates into what kind of a sources and sinks you want to place, or should I increase the strength of the source and sinks along the airfoil. Okay, and that finally translates into the thickness distribution of the airfoil, because the strength of the sources and sinks influences the derivative of the thickness with respect to x. All right. Okay, so let me just give you an example, right? So for example, if I'm saying the peak suction over here, I want it to be a little bit stronger. I want the pressure to be even lower over here. What should I do?
The stronger, increase the magnitude of the sources at the front. Yes, because I know the reason there is a flow acceleration over here is influenced by this source primarily, right? So if I want this higher suction over here, then I want to increase that source. Now, what is the effect of increasing that source?
It increases the thickness.
It increases the rate of thickness increase near the leading edge, right? It makes the leading edge even fatter, less sharp than this one, right? So basically, I get there like a whale-like airfoil if I want the peak suction near the leading edge to be large. So let me just make a whale-like airfoil. So I'm going to increase this to 20, and in order to balance it out, I just want to increase the strength of the sinks. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay? So that's the airfoil I get, right? Let's wait for this flow to come back. So essentially, I get a lot bigger leading edge radius. All right. So this is going to further decrease the peak suction over here, right? Instead of minus 0.17, I get minus 0.242527, right? So that's what I get. Okay, so this is symmetric airfoils, and we don't really care about symmetric airfoils at zero angle of attack because it doesn't really generate any lift, right? So what we really care about is the either asymmetric airfoils with a camber or symmetric airfoils at non-zero angle of attack because these generate lift. But the placement of sources and sinks is a very good exercise because in order to get non-symmetric airfoils, we need vortices, and the placing vortices is slightly more complex than placing sources. So let me just summarize at this point. So strength of source is proportional to d thickness dx, right? So that's basically how we place sources. And so that's how the strength of the sources and sinks affects the shape of the airfoil. And in addition, okay, the sources basically creates acceleration. So source creates acceleration downstream and deceleration upstream. Okay, and again, acceleration means suction, deceleration means high pressure, right? That's basically Bernoulli's. We are in the fantastic world of incompressible potential flows. All right. So what we can see is that the sources and sinks affects the shape and the pressure distribution in two different ways. It affects the shape locally. Okay, so whenever you increase the source strength of the source, it changes the d thickness dx at that location, at that chord location. But it changes the pressure distribution in a non-local way. Okay, so it affects a range. If you increase the strength of a source, it decreases the pressure on the range downstream. It increases the pressure on the range upstream. Okay, so a local effect on the shape, non-local effect on the pressure. We're going to see vortex is exactly the opposite. Okay, if you place a vortex in the flow, it changes the pressure distribution locally immediately at that point. So think about it, right? So if you go back to the flow, and let me just make a place 0 at that location. Let's change this to a vortex. And make the vortex, I don't want to be too dramatic, maybe a little bit more. Okay, make it 20. What we are going to see is that it changes the pressure distribution almost immediately, right? Because of the rotation, it accelerates the flow below and it decelerates the flow above. So the effect of a vortex is local on the pressure, but its effect on the shape is non-local. Okay, it affects the shape in that it actually makes the flow go down upstream and make the flow go up downstream. So essentially, it creates a camber. it creates basically a negative decamber dx upstream. It creates a positive decamber dx downstream. Right, so a vortex is exactly the opposite. So now we are getting into how do we calculate asymmetric flows around the airfoils by placing vortices. Vortices, so vortices decrease decamber dx upstream, okay, and increase decamber dx downstream, okay, but its effect on the pressure and the velocity is immediate. So it basically it decreases velocity above that vortex and increase and accelerates the flow below that vortex. It's a local effect. Okay, and the decreasing the velocity above means high pressure above, and increasing the velocity below means low pressure below. Alright, so basically by placing a positive vortex, you are generating negative lift, right? And you're generating negative lift at the location of that vortex, right? So basically by placing a vortex here, I am generating negative lift at that location. So basically that negative lift is centered at that location of that vortex. Agreed? Okay. So the connection from the strength of the vortex to what lift you get, what pressure distribution you get, and where that lift is pretty obvious, right? So if I want to lift centered at the quarter chord, I would be basically make that 0. If I want to lift centered at the middle of the chord, I would make is that the middle? Yeah, I think that's the middle. So I would make this. Let me just still make a close the airfoil and then I would make this a vortex, and if I want positive lift, I would give a negative vortex over here. So that's how I'm generating positive lift, and that lift is centered right over here, right? And you're gonna see that I am gonna be creating a cambered airfoil over here. So this now starts to have a camber, but it's totally not obvious what the camber is, right? We know that by placing a vortex here, it's creating the camber is sloping upwards, upstream of that vortex. It's sloping downwards, downstream of that vortex, right? But like, if you want a particular camber, it's a little bit hard to place the strength of the vortices to get that camber. Okay, is it clear what how the effect of sources and sinks and vortices are? Right, source and sinks are very easy to place according to the shape, but the calculation of the effect on pressure is more difficult. Vortices, the effect on the pressure is immediate and pretty obvious, but calculating the effect of a vortex to the shape is not so obvious. Okay, even though it's not obvious, we still want to figure out a way to reason about it. And we are going to be doing 2 separate exercises. And the first exercise I want you to work on is, first of all, let's change all the sources to vortices and see if we can start to simulate the flow of an airfoil with no thickness. So that doesn't require any source and sinks, right? We're going to be changing everything to vortices. And I want to figure out if you can simulate the flow over just a flat plate with no thickness, but at non-zero angle of attack. So let's change the V to let's just a 0.25. Okay, so I get a pretty significant angle of attack. It's more around between 10 and 15 degrees angle of attack. It's closer to 15. All right, so you're gonna see, okay, without enough vortices, the flow would just go through the flat plate, right? Okay, so that's not a physical situation. Can you, by changing all these sources and sinks to vortices of different strength, to make the flow go basically parallel to the flat plate? How can you do that? Okay, so basically we want to change all the sources to vortices, okay, and try to make the flow go parallel to that flat plate from the leading edge to the trailing edge. Okay, just I think it's easy to go here. Remember, we are also not doing this at random, right? If you place a vortex here of, see, what strength am I doing? Of positive strength, that makes the flow go. If you use the right-hand rule, like positive vorticity is pointing out of the board, it makes the flow go up downstream of it, and makes the flow go down upstream of it. Right, so here, for example, we find the flow to be going through the plate up. So we want more negative V, right? So we want to make this vortex to be more negative. And for example, let's make it minus 6. Okay, now you're gonna see it's a little bit better downstream of here, right? The flow is no longer going through the flat plate at such a high y velocity, so maybe even higher, minus 16 or minus, just to make it minus 20. Okay, now you're going to see that at least locally, the flow goes more parallel to the flat plate. And then you can see over here, the flow goes through the flat plate at even higher velocity, right? So that doesn't work. And to fix that, the thing to change is this vortex. You want this vortex to counter the effect of this vortex and remove the flow. So what I would do is I want to make this also minus 20. And right, it's seems to be slightly better, but the flow is still going through. So maybe minus 20 is not enough. I would do minus 30. Okay, now it's pretty good, right? Now it's pretty good. So basically, and you can work more downstream to make the flow go parallel. And you may have to go back and forth because the effect of changing one vortex is the effect is not local, right? It will affect a lot more neighbors. Okay, so this is the flow I got by playing with it a little bit. I think I need a 0.25 velocity, y velocity. Okay, so one thing I want to clarify is the effect of adding a non-zero y velocity at the free stream. Okay, in aerodynamics, there are two things we can do that are equivalent. One thing is to physically rotate the airplane while keeping the free stream to be the same. Right, that increases the angle of attack. The other completely equivalent thing to do is to rotate the world and keep the airplane exactly the same. So that is basically changing the free stream velocity to have an angle that points upward. That's completely equivalent of rotating the airplane with a higher angle of attack, right? You just rotating the wheel, the frame of reference. In wind tunnel, of course, it's much easier to rotate the model than rotating the whole wind tunnel, right? But in a calculation like this, and we are going to see later in a CFD, computational fluid dynamics, usually the latter is a lot easier. So instead of going manually change the location of all these vortices, right, it's actually much easier just to change one number, change the y velocity to simulate the angle of attack. Just imagine what you have to do if you want to rotate the model, right? You have to really do sines and cosines and change the x and y of all these vortices. So that's why, like in a calculation, the more common thing to do is to change the free stream rather changing the model. Okay. Essentially, this free stream indicates an angle of attack of closer to 15 degrees, right? Did anybody do a arctan calculation to see what arctan of a quarter is? What? Should be closer to 15 degrees if I'm not too wrong. All right. Anyway, so this flow, as you can see, I didn't do it that well, very much downstream, so the flow is going too much downward at the end. But I think I did it reasonably well from here to here, where the flow is going down a little bit, but it's not too bad. I think if I maybe change this to -2, it'll be slightly better at the end. Maybe -3, -4. That might make things a little bit better at the end. Anyway, so basically, this is the vorticity distribution, right? That makes the flow go parallel around this airfoil. And as you can see, did anybody get a distribution a little bit like that? Yeah, you did?
Yeah.
So how would you characterize that distribution? Is it anything familiar? Not really, right? But what you get is something relatively flat at the second half, but really goes to very high strength towards the leading edge, right? You get the same trend? Yeah, anybody else got the same trend? So this is, again, this function, as you can see, of course here we are doing these things manually, so we only had something like 19 vortices. In a computer calculation, you can place like 190 vortices or even 500 vortices and solve for the strength of the vortices so that the flow is exactly parallel, right? And if you do that, you get a function that is pretty similar in spirit to this distribution. And that function is very important in aerodynamics. Why is that the case? The primary reason is actually two reasons. One reason is the linearity. So let me illustrate the linearity by asking, if I increase V infinity by a factor of 2, so if let's make it make sense is to decrease it by a factor of 2. So if I make V infinity 0.125, would the flow still be parallel to the airfoil or not? No, right? Because the flow would be going down across these airfoils because I decreased. The flow is the sum of multiple elementary flow fields, right? I didn't change these flow fields. I only changed the free stream component. So that means now the free stream doesn't have enough y component to stay parallel, right? The flow is going down. through the flat plate. Now, how would I change the strength of the vortices so that the flow is still parallel? Yes? I would have to decrease the magnitude, but exactly how much? Half, right? Because if I half everything, right, that makes the v velocity still exactly equal to 0, right? The y directional velocity over here is just the sum of all the individual components. If it's originally equal to 0, if I half all the components, it's still going to be equal to 0, right? So basically what I need to do is just to go through all the strengths and make them half to make the flow still parallel. I'm not going to do it, but like you can see, that's going to be true, right? And if I double the y velocity, I can just double the strengths to make the flow still 0 across in the y direction across the flat plate. So it's linearity. That means if I increase the angle of attack by a factor of 2, the lift increases by a factor of 2, right? Because the strength of the vortices, as you remember, right, like affects the difference in the flow velocity up and down. Okay, if I increase the strength of the vortex by a factor of 2, I increase the difference in flow velocity by a factor of 2. Okay, and that increases the lift by a factor of 2 without changing the distribution of lift at all. Do you agree? So because at every location the vortex just increases and the pressure difference at that location just increases by a factor of 2. So there is no effect on the distribution of the lift except for doubling the lift if I increase the angle of attack by a factor of 2. The other important reason why this function is important is that the same distribution applies for any airfoil, not just a flat plate. If you just add that exact distribution with the set of sources and sinks, so that's, I mean, it's a huge array because I get a bunch of vortices and I get a bunch of source and sinks. The source and sinks is exactly what we worked out for the NACA double 12 airfoil. The vortices is the same distribution as I was looking at earlier. And of course it's a mess, but if I increase the angle of attack to the original value, you're gonna see that I actually get a NACA double 12 airfoil at this about 15 degrees angle of attack. So the function that determines the distribution of vortices is exactly the same if you just add a thickness to the airfoil, and it doesn't depend on what thickness distribution you're looking at, right? Basically, the vortices determine the camber and angle of, let's forget about camber. We're going to be talking about camber next week. The vortex distribution determines the angle of attack. Okay, and if you increase the angle of attack, you just increase all the vortices strength proportionally. And the distribution of the source and sinks determines the thickness and thickness only. So they are independent. Okay, so this is what's universal about that function. And so one of the results that can be worked out analytically is the location of the center of lift for that distribution. So if you just think about this, right? Because if I have a strength of minus 45 here, then I'm basically creating a lift over here proportional to 45, right? And if I have a strength 20 here, then I have a lift to force proportional to 20 over here, and then a lift to force proportional to like 12 and 8 and 6, etc. here. So basically I have a high lift over here, less lift over here. If you think about the total effect and balance the total lift at some point, where do you think that point is, roughly? So basically, a force of this at this point, a force of this at this point, etc. Right? Where is the balance? Where is the center of lift? Close to where? Closer to the front, for sure, right? And where do you think? Just take a guess.
Maybe like between the second and third point.
Maybe between the second and third point. So if you do aerodynamics, a very important location is actually the center of lift derived from this function. You can work out analytically. This is exactly at the quarter chord, like a quarter from the leading edge, halfway between leading edge and the middle of the chord. Okay, this is universal because the function is universal. For any airfoil, okay, for any symmetric airfoil, if you put it at an angle of attack, you get a lift distribution that is exactly that function, and the lift is going to be at the quarter chord. Not only that, but also for asymmetric airfoils, the lift will not be at the quarter chord. We are going to be discussing it next week. But if you change the angle of attack by increasing V infinity, right, then you would actually get a uniform velocity. So if there is no V infinity, even for arbitrary airfoil, you get an airfoil where the flow is tangential to the surface, and you increase V infinity, what happens? What happens is you add this V infinity to all the flow velocities everywhere, right? So the flow actually goes across the airfoil at that V infinity. And to balance that, you add exactly the same distribution of vortices on the airfoil to simulate the increment in angle of attack, not just for symmetric airfoil, but for any airfoil. So this function that it's non-trivial to work out, but is extremely important. I mean, that's like the thing that matters in the aerodynamics of airfoils. Just to end the lecture, I'm just going to tell you this is actually definitely the most useful tool for designing airfoils. It's called Xfoil. If you take any, the most useful, easy to illustrate is using a very thin airfoil, Naka 006. It's very thin, right? And put it at 1 degree angle of attack. You get the pressure distribution, and the difference between the two upper and lower surface is really the vorticity strength. And this function is that distribution of vorticity you get. It's very high near the leading edge, and it shrinks and it becomes 0 at the trailing edge. So that is the function you guys can reconstruct by placing these vortices. Okay, so see you in recitation on Friday, and again, just a reminder, there will be an in-class quiz next Wednesday. All right.